Problem number 25. S is the surface parametrized by R of u. V is V cosine u, V sine u for the bounds given. First thing we have to do is choose the picture. So first thing to kind of notice here is that y is just given by V. As we move along the y-axis, the cross sections here will be circles. You know, x is cosine u, v is sine u times v there. It's going to be circles parallel to the xz plane. So there was a previous take of the video. You can already see what the answer is going to be. Like, this isn't giving us circles along the y-axis. These are giving us something like that. And the thing to tell here, it's going to go all the way around the circle. U is running from 0 to 2 pi, so not that one. Does it look like these kind of circles or that circle? Well, the radius of our circles, V, grows linearly as y grows. And so that's how we settle on this one. Okay, so that is part A. To find a parametrization of a tangent plane, well, to find a plane, we need a point and a normal vector. We already have a point given to us, the 1, square root 2, and 1. How do we find a direction vector, a normal vector for our plane? Well, we're going to calculate r sub u, r sub v, take cross products, take partial derivatives here, and then take a cross product of these two. So partial derivative of this respect to u will be, let's see here, minus v sine u, 0, and v cosine u. Partial derivative of this respect to v will be cosine u and 1 and sine u. So now we have to take a cross product of ru and rv. This will give us a normal vector. Okay, minus v sine u, 0, v cosine u, 1, and sine u. Okay, so we end up with the I hat component is 0 minus v cosine u. The j hat component will be v cosine squared u plus v sine squared u, just becomes v. The k hat component will be negative v sine u minus 0. So this is our normal vector. Well, we have to find a normal vector at a particular point, at the point 1, square root 2, and 1. So x, y, z are 1, square root 2, and 1 here. So really, x is given by v cosine u, y is given by v, z is given by v sine u in our parametrization. So we can tell here y has to be square root 2, so that just gives us v is square root 2. And then for x and z, well, v is square root 2, then cosine u needs to equal 1. And then z is v is square root 2, sine u also needs to equal 1. This will be satisfied if u is pi over 4. So when u is pi over 4, cosine u and sine u are both 1 over square root 2, and you satisfy this. Okay, so we know what value of u and v give us this point here. So let's plug that in. Let's plug that into our normal vector here. We would end up with negative v is negative square root 2 times cosine of pi over 4. And v is square root 2. And then we'd have negative v, negative square root 2 times sine of pi over 4. Of course, cosine of pi over 4 is 1 over square root 2. Sine of pi over 4 is 1 over square root 2. So this just becomes minus 1 square root 2 and minus 1 as our normal vector. So we have a normal vector, we have a point. So easy chapter 12 problem. What do we conclude here is that we conclude our equation of the tangent plane is negative 1 times x minus 1 plus square root 2 times y minus square root 2 minus 1 times z minus 1 gives us 0. So that's part B. Part C, we're asked to find the average value of the function f of x, y, z is equal to y on our surface. Well, so to find average value, so that would be 1 over the surface area of our surface times the integral over our surface of y ds. Now, we're told that the surface S is area 4 square root 2 pi, so really all this has to do is calculate out this surface integral right here, scalar surface integral. To do that, well, we've done a lot of the work right here. We've got the cross product here, so let's just find the magnitude of our cross product, because we'll need that. Magnitude of r sub u cross r sub v. Not in this particular case, but more generally, it's given by the square root of negative v cosine u squared plus v squared plus negative v sine u squared. And this becomes, when there's a v squared cosine squared u plus a v squared sine squared u, that's just this v squared plus another v squared. V is non-negative on the domain that we're talking about, so we can just say that this is square root 2 times v. Okay, so why did we need this? Let's go to a new slide here. The double integral, the scalar surface integral of y ds. Okay, our bounds on this were u runs from 0 to 2 pi. V runs from 0 to 2. Y gets replaced by V in our parametrization. And then we throw in a factor of the absolute value, the magnitude of our normal vector. V times square root 2 times V, dv du. Okay, so if we integrate this, the u integral will just give us a factor of 2 pi. And that can move outside, square root 2, just the integral from 0 to 2, v squared dv. So this would be 2 square root 2 pi, and this ends up here as v cubed over 3, plug in 0 to 2, and so that will give us 8/3. So we have 16 square root 2 over 3 pi. So our final answer for the average value we said is the value of the integral divided by the surface area. So average value is 16 square root 2 pi over 3 divided by the surface area. We read it off of our worksheet, 4 square root 2 pi. And if we want to simplify, a bunch of stuff will cancel. And so it looks like 16 over 12 is 4/3. Okay, that is problem number 25.